Hi, everyone. The purpose of this lecture is to record the lecture from last Thursday, Thursday the 21st. Unfortunately, I forgot to press the record button, and the lecture didn't get recorded, so I'm doing this lecture so that anyone who wants to can watch this lecture. And so I'm going to go ahead and share my screen. Okay, I'm going to go ahead and okay, here we go. So this is the slide that we stopped at our previous lecture. And if you remember in our previous lecture, we were talking about objective functions. We were talking about finding maximum and minimum of an objective function. And we played a game. We played a game where we had a function, and we were sort of given a function and a design space, and the game was to find the location of the minimum of that function without knowing much about the function. And we were did a sort of trial and error method where we finally got close to finding the minimum of the function. And what we're going to do today is we're going to kind of formalize that method, mathematically formalize that method. Starting here. So if you have an unconstrained problem and you have some function f of x, which is a function of only one variable x, it's very easy to go ahead and take the first derivative of that function and find all the places where the first derivative equals to 0. In this case, it's a, b, and c. And then you can take the second derivative at that location, or those locations a, b, and c. And depending on the sign of the second derivative, you can go ahead and determine whether it's a minimum or maximum. The problem becomes significantly more complicated when you have a constrained problem like this graph on the right. In this case, you have the same function f of x, but it's subject to these constraints g1 and g2. If you take the first derivative of f of x between g1 and g2, you get basically point B is the only place where you get close, the only place where you get a 0, and that's what it was meant to look like. And at that point, you don't have a maximum or a minimum, so the first derivative method doesn't work. In fact, the maximum and minimum of these equations lie at these little places where the function intersects with g1 and g2, and at that point, the first derivative is definitely not equal to 0. So in order to find the maximum or minimum of a constrained problem, the mathematicians have developed these other methods like gradient method, genetic search, particle swarm method. And these are ways of determining the minimum maximum of that function or a function subject to constraints. There are many more methods, and there are people out there whose research passions focus on numerical optimization, and some of these people even participate in competitions where they kind of all go in a room and are given a function, and then they unpack their algorithms and they determine, they have a competition to see who could find the optimum of that function the quickest. So they have these algorithms that they modify and continue to improve to find the best fastest way to find maximum and minimum of an equation. So we're going to talk about the gradient method now, and I'm going to kind of show you like a formal mathematical way of how the gradient method works. So suppose you had the following problem. You had the function f of x that you wanted to minimize, and it's subject to the constraint g of x has to be less than or equal to 0. On the right here, we've got a graph of the design space of x2 and x1, and we have the f of x function plotted here in black, and we have the g of x constraint plotted in blue right there. And the design vector, that's the location in the design space, is defined by this x here. And then we have this equation here, which calculates out the design vector as a function of search direction and length of step. The search direction in this gradient method, or also called steepest descent or steepest descent, is defined by this vector S. S points the direction of the search. The method starts by finding the gradient, okay, of that function f of x at some starting point, in this case x of 0. And the gradient points in the direction of steepest ascent or steepest descent, depending if it's a maximum or minimum. And it also is perpendicular to the function at that point. So this curve, this line right here. The search direction is chosen as the opposite of the gradient at that point. So this is the S direction, and then the alpha. The step is defined as how far you go along this straight line right here. In this case, in this problem, the search direction is in -1 and -0.5. Here is the mathematics that we're going to go through to show you how this works. So the initial position is for x, the initial design vector is 2 and 1. Plugging this value into the equation is straightforward. For the initial point, we'll choose an alpha equal to 0 because it's the starting point. We'll go ahead and plug in the the search vector S and the design step 0. And the design step is 0, so we don't go anywhere. So the initial position is 2 and 1. At that point, the value of the objective function is 10, and the constraint at that point is equal to -1. So this is okay. Remember the constraint has to be less than or equal to 0. So you have not violated in this case, you have not violated the constraint. Next thing is we choose sort of randomly a step length. Let's choose a step length of alpha equal to 1. Then by plugging these values into the location of the new design vector, we get a new design vector is at 1 and 0.5. That's the location of the new design. And in this location, the objective function is equal to 8.4. So this is good. We've gone down. We'll go ahead and calculate out g of x, or g of alpha actually, at that. So this is the constraint at that location. It's equal to -0.2. So the constraint is not violated either. Everything's okay. We then get more aggressive and we take a larger step with alpha equal to 1.5. Plugging those values into our equation, we get a objective function of 7.6. So this is even lower. This is good. But the problem is that the location or the value of the constraint at that value is 0.2. So we have violated the constraint because it is now greater than 0, which it can't be. So we have to dial back a little bit. We reduce our step to a 1.25. Plugging those numbers in, we get an objective function of 8.0, which is good because it's less than 8.4 and less than 10. So we know that's closer to a minimum. And then at the constraint is equal to 0 at that step length. So this is just meeting the condition, and this is actually the minimum for this problem, for this function f of x. So this is with two variables. This method is obviously very straightforward. It's not very difficult from a computational perspective. It's not very difficult from a mathematical perspective. It's pretty straightforward, no problems, right? So it's not that interesting really. But what's nice about this is that it can be expanded to infinite number of variables. And of course, you and I can't do that sitting here, but computers obviously can take in this method, turn it into an algorithm, and then solve this problem for hundreds of thousands, millions, whatever, of different variables. And so this is a method, this gradient method or method of steepest descent or steepest ascent. This is a method that is very amenable to being programmed into a computer and using an algorithm to find the optimum of the function. It's useful to define feasible regions and usable regions. The usable region is shown here by this blue curve, and the usable region is any place where the objective function decreases. And if you think of the gradient, like I said, it's perpendicular at that point to the function. So here's the blue line here, and this is this right here. This is perpendicular to that function at that point. It's perpendicular to the tangent, I'm sorry, of the function at that point right here. And then it's reasonable to say that that anytime you are, let's say, below this red line, your function will decrease because it's going the opposite direction of the gradient. And so anywhere on this line, in this angle right here, okay, anywhere in here, so anywhere where the search direction S is between 90 and 270 degrees. So this is useful to us because then we can mathematically define the dot product of the transpose of the gradient times the search direction has to be less than or equal to 0. And this is because the dot product is the two vectors, the magnitude of the two vectors, or the product of the two vectors times the cosine of the angle between them. And cosine is negative between 90 and 270 degrees. So it's very convenient to say, okay, the usable region is any place where the dot product of the gradient of f of x and s is less than or equal to 0. Next is the feasible region. So the feasible region is any place where you don't break or violate the constraint G. And a similar approach is used here. You can imagine drawing another tangent right here so that the gradient of G at that point points perpendicular to the tangent of the curve at that point. And if that is, if the dot product of the search direction and the gradient of G of x is less than or equal to 0, then that is a feasible region. Okay, right here. So the overlap between the usable sector and the feasible sector gives you the usable and feasible sector, which is the best direction in which to search. So that's the best direction to point your S vector. And this is usable, or this is, I should say, this is convenient because it allows your algorithm to operate much quicker. It sort of reduces the number of possible directions in which you can search. And this goes to making faster algorithms that get you to a solution quicker. So that's part of playing the competition, right? How do you solve as quick as possible? Another useful concept to define is the conditions for optimality. So this is also useful in your algorithm. So in order for your algorithm or you to know when you've hit that optimum of the equation, if you meet a certain condition, a certain set of conditions, then you know that you've hit your optimum, a maximum or minimum. And a necessary condition to finding this location in the design space is given by this equation here. Basically, it says that the sum of the gradient of the objective function plus the gradient of the constraint times a constant lambda called a Lagrangian multiplier lambda. The sum of those must equal to 0. And physically, what this is saying is that you will hit an optimum when the gradients of the objective function and the gradient of the constraint are parallel to each other. Okay, and because, like down here, you see it's the same thing as this graph over here. Because these two gradients are parallel, you know you've hit an optimum. Okay, but because the magnitude of these gradients aren't necessarily going to be the same, you need to multiply the constraint by this lambda, this Lagrangian multiplier lambda. And then when you add those two together, they cancel out. And that's when you know that's a necessary condition in order to find an optimum. And this can be formalized into this theoretical basis for optimality, the Karush-Kuhn-Tucker condition. And this is pretty much the same as what we've seen before, just a little bit more formalized. And so here we have a design space of A1 and A2, an objective function of W. So I've switched variables on you here. The objective function is now W instead of F, and the variable is A instead of X. So if you have this, the requirements are to optimize W subject to the constraint that the constraint G of A is equal to 0. Assuming this is a constrained problem, you can't use the first derivative, so you need to find some other way to make sure or determine if you've hit an optimum. And so there are three conditions that must be met mathematically in order to ensure that you're at an optimum. The first one is that the design vector at that optimum, A star, is in a feasible region, okay? And then the lambda, the Lagrangian multiplier lambda, has to be greater than 0. Okay, and then this next equation here is really just a more generalized version of the equation you saw on the previous page. And it says that the sum of the gradient vector of the objective function plus the sum of all the gradients of the constraints times these Lagrangian multipliers lambda must all add up to equal 0 to get to an optimum. Let me delete this. Okay, so if this is kind of nicely graphically shown right here. Suppose you have this function w, which is in blue here, and you've got these constraints g1, g2, g3, which are shown in black, and you see that the g3 doesn't really play any role because it's way over here, and you know, kind of intuitively right here is this is the optimum point right here. And if you look at the gradients for G1 and G2 at that location, they go these different directions, okay? But if you multiply them times these Lagrangian multipliers, L2 and L1, then they can resolve into a vector that is parallel, but not necessarily the same length as the gradient of W, okay, the objective function W. So therefore the tangents at this point, A star, for the three constraints, or sorry, the two constraints and the objective function are parallel, and the gradient of W and the resolved gradient of the constraints G times these Lagrangian multipliers cancel each other out. So that is a necessary condition for optimality. It doesn't necessarily say that you have an optimum. It just says that if those conditions aren't met, then you don't have an optimum. But this is useful for a computer algorithm to use. So how do we use this? How do these algorithms use this concept in order to find the value, a point in a design space that is an optimum? So here we have an example on the right here. This is from Geert Vande Plas. I'll introduce him in a minute. And so this is a design space of X1 and X2. It's more complicated than some of the stuff I've shown you before. And so you start your optimization problem by choosing a location within the design space. In this case, we've chosen this X0 right over here. The procedure is to calculate out the gradient of this objective function f, we'll call this f, right here, okay, at this point, it's facing this direction, and then choose a search direction, which is the opposite of that gradient, and then pick some step length. Boom, so now you're over here, and you can calculate out, did my objective function go down? In this case, we're minimizing, we're going down this way, this is downhill. So did it go down, yes or no? It did, so that's great. So then the next thing you can do is, the next thing in the procedure is to calculate out the gradient of this new X1 right here, which is pointing this direction. And then choose a search direction, which is the opposite of that, and then take a step of some length alpha. Now you're at this X2 location. And then you can go ahead and calculate out the value of the objective function at that point and determine if you have if your value of the objective function has gone down. And then you can keep doing this on and on and on and on until the problem is called it converges, which means that the value change in f of x stops going down so quickly. You keep doing this, calculate out the calculation of the search direction and the step, and calculate a new value for the objective function f in this case, and you're not going down anymore. You're going down by very tiny little slivers, and that's the point where the problem is set to converge, when you found, in this case, the minimum of this function. There's other search methods. One that's kind of interesting is called the genetic search algorithm. And in this method, you have, again, a design space, and you choose a population of what are called individuals. So the individuals are defined by, say, zeros and ones, and you can use multiple digits, but these correspond to some location within the design space, and you can kind of seed think of seeding your design space with many individuals, and they each have some value for the what they achieve as far as the objective function is concerned. The next procedure is you have sort of a mating between these different individuals, like all of them, they mate with each other, 2 by 2 by 2, right? And then you produce a generation of offspring, children. And then for each of these children, you have a procedure which somehow combines some of the good things, or combines the zeros and ones in some way, in some algorithm of these parents 1 and 2, and produces these offspring. And then there's what's called a mutation. And then for each of the children, the value of the objective function is calculated. And some children will have a higher objective function, some will result in a lower objective function. Okay, and then there's the possibility that maybe you'll violate a constraint, and then there's a penalty function to account for having violated a constraint, so that child maybe doesn't look like they've achieved a super great value of the objective function. And the next step is to take these group of children, look at the ones that have lowered the objective function, and then have those two breed with each other to have an offspring, a second generation of children, and then determine for each of those offspring what their value would correspond to in the design space. And then you keep doing this over and over again. And so again, you hit a convergence. That's a point where the successive generations of children don't lower the objective function by very much. But this is called genetic search. Another similar method is called particle swarm. And this is a procedure where you assume the design space is seeded with many bees that are kind of sort of randomly located over the design space. And then each of these bees chooses a direction. Okay, direction is to look for food. Okay, more food would correspond to a better value of the objective function. So each of these bees within this swarm of bees in your design space is assigned a search direction, or search direction and speed. So they call it velocity, because velocity is a vector value. And then you find a new location for these bees after step 1, and then you calculate out, okay, which velocities increased or decreased the objective function, depending on what you're trying to optimize for. And then again, there's a procedure for what happens if you violate a constraint. It's a penalty function. And then there's a second set of flights for each of these bees, and then you keep moving in the directions that get to a minimum or maximum, an optimum. And the velocity direction is shared with all the bees. So the the successive steps of velocity are taken into account when selecting the new velocity directions after the first go through. And this is also an interesting method of finding an optimum for a function. Each of these methods kind of have their plus and minuses. There's advantages to each. So if you compare the advantages and disadvantages of gradient methods versus these sort of genetic and particle search methods where you're kind of seeding the design space, the gradient methods are less computationally intensive, and they take less time to converge than the other methods. But the other methods, the genetic search and the particle, are more likely to find a true global, within your constraints, global optima. And they're also a little bit easier to program. And then finally, if you're, a lot of the gradient method really depends on your design space not having any sharp cusps or anything like that in the design space. So the derivatives are all continuous. So the genetic search method kind of sidesteps that problem. Particle swarm kind of sidesteps that problem. So in a lot of cases, you can find more cleanly the location of, or I'm sorry, you can much better handle if your design space is discontinuous, places where the first derivative might blow up. Moore's law. So this graph this shows that the ability of these algorithms to handle bigger, more complex problems has scaled with the scaled with Moore's law. That is, as computer power has become cheaper, faster, easier to obtain, the number of variables that an optimization algorithm can process has gone up. Right here, you see this point. It says big dot, 500,000 variables. That's the that big dot program is a souped up hot rod, I don't know what you want to call it, algorithm developed by Geert Vanderplots, who I'm introducing in the next slide here. And that apparently is one of the fastest, most capable algorithms out there for handling numerical optimization. So with that, I'd like to introduce Geert Vanderplots. Again, I'm introducing you to these various people because if you want to learn more about these various topics, you can now easily go to the library and look up under their names, and you'll get a bunch of papers. And if you're interested, you can go ahead and obviously read those and learn more about, in this case, numerical optimization. So Geert Vanderplots went to Arizona State for undergraduate, and he, I've met Geert Vanderplots a couple times, and he said he didn't get real great grades in high school, so he went to Arizona State. However, he's a brilliant man, and apparently his professors noted that he was a brilliant student, and he got a ride to get a PhD at Case Western Reserve. His advisor was Lucian Schmidt, who I've introduced you to previously, and he worked on various numerical optimization, structural optimization problems, most of them for NASA. After he graduated, in fact, he went to work for NASA. He was there for many years. He worked on Solution 200 of Nastran, which is a optimization module within Nastran. After that, he was a professor at the U.S. Navy Postgraduate School. He went on to then be a professor at the University of California, Santa Barbara. He did a lot of good work there. And then finally, in 1987, he founded the company Vanderplots R&D. Vanderplots R&D specializes in software that completes or finds numerical optimization optimum, and then combines that with finite element codes to complete what's called structural optimization, which we'll talk about in the next lecture. And he is really a pioneer and a world leader in structural synthesis and multidisciplinary optimization, numerical optimization development. And the name of his structural optimization software, or Vanderplots' structural optimization software, is called Genesis. And I've used it many times. It's very interesting how I don't know, you can really come to solutions that are unintuitive. So that is the end of today's lecture, or actually makeup lecture for Thursday the 21st. And I will look forward to seeing you folks on Thursday morning this week. That's what is that, the 28th? And in next week, we will start to talk about how these numerical optimization tools are combined with structural analysis tools like finite element analysis to guide design engineers in finding optimum design. Thank you very much. See you day after tomorrow. Bye.